For thousands of years, a city was mostly physical. Buildings, roads, markets, bridges, water systems, power lines, and people. The city existed as a collection of structures, separate systems, connected by infrastructure. But the next generation of cities is being designed differently. The city is becoming intelligent. Sensors observe movement. Networks transmit information. Algorithms analyze behavior. Artificial intelligence predicts demand, and automated systems respond. Traffic can be monitored in real time. Energy can be redirected. Buildings can adjust their own systems. Vehicles can communicate with infrastructure. Waste can be tracked. Water can be measured. And entire districts can be managed through data. The city begins to behave less like a collection of buildings and more like an operating system. Every road becomes a connection. Every building becomes a node. Every vehicle becomes a data source. Every utility becomes part of a network. And every movement creates information. This creates a new possibility, a city that can observe itself, analyze itself, and continuously optimize itself. But the moment a city becomes a system, a new question appears. Who operates the system? Who owns the data? Who controls the infrastructure? And who decides what the city should optimize for? Because the smart city is not simply a more advanced city. It is a new architecture of power, and the blueprint is being designed now.
Every intelligent system begins with observation. Before a machine can optimize, it must know what is happening. This is why the future city begins with sensors. Sensors embedded in roads, buildings, vehicles, power systems, water networks, public infrastructure, and communication systems. They measure movement, temperature, air quality, energy consumption, traffic, noise, water usage, and demand. The city begins to generate a continuous stream of information, not once a day, not once a month, but every second. A traffic system can detect congestion before a human notices. An energy system can detect demand before the grid becomes overloaded. A building can detect occupancy. A water network can detect unusual consumption. The city becomes measurable, and what can be measured can be optimized. This is the foundational promise of the smart city. Turn the physical environment into data, then use data to make the environment more efficient. But observation creates something else: visibility. The more sensors a city deploys, the more the city can see. And the more the city can see, the more decisions can be automated. The sensor layer is therefore more than infrastructure. It is the beginning of urban intelligence. The city does not need to understand everything. It only needs to collect enough signals to predict what happens next.
A city is difficult to experiment on. You cannot simply redesign an entire road network and see what happens. You cannot shut down a power grid to test a new strategy. You cannot move millions of people to evaluate a new transportation system. The physical city is too large, too expensive, and too important to use as a laboratory. So the next generation of urban planning is moving into simulation, the digital twin, a computational model of the physical city, a virtual version of buildings, roads, energy networks, transportation systems, and infrastructure. The model receives real-world data, then attempts to reproduce the behavior of the city. What happens if traffic increases? What happens if energy demand doubles? What happens if a bridge closes? What happens if a new district is built? The city can be simulated before the physical world changes. This creates a new form of urban intelligence. The city becomes a feedback loop. The physical environment generates data. The data updates the digital model. The model generates predictions. The predictions influence physical decisions. And the new physical conditions generate more data. The city begins to learn about itself. This can make urban planning more precise, but it also creates a new dependency. The more decisions rely on the digital model, the more important the model becomes. The city is no longer governed only by what exists physically. It is increasingly influenced by what the system predicts.
A modern city contains thousands of systems: transportation, energy, water, waste, security, healthcare, communications, buildings, and commerce. Historically, these systems operated separately. Different companies, different technologies, different databases, different control centers. The smart city attempts to connect them. This creates an urban operating system, a layer of software that allows different parts of the city to communicate. Traffic data can influence transportation. Transportation data can influence energy demand. Energy data can influence building operations. Building data can influence emergency response. The systems become connected, and connection creates coordination. A city can respond faster. Resources can be allocated more efficiently. Problems can be detected earlier. Theoretically, the city becomes more intelligent. But integration also creates concentration. The more systems connect to one operating layer, the more important that layer becomes. If the operating system fails, multiple services may be affected. If the operating system is controlled by a small number of companies, a city may become dependent on external infrastructure. This is one of the central questions of the smart city. Who owns the operating system? The city? A technology company? A consortium? A private infrastructure provider? The answer determines more than software ownership. It determines who controls the architecture through which the city operates. And when infrastructure becomes software, software becomes governance.
Traditional infrastructure waits for people. A traffic light follows a schedule. A maintenance crew responds after something breaks. A utility company reacts after demand increases. A delivery truck follows a human route. The autonomous city operates differently. It responds in real time. Traffic systems adjust based on movement. Energy systems respond to demand. Vehicles communicate with roads. Buildings optimize their own consumption. Robots move goods. And artificial intelligence coordinates thousands of decisions. The city becomes responsive. Instead of waiting for a problem, the system attempts to predict it. Instead of sending a human to inspect every situation, sensors identify anomalies. Instead of following fixed schedules, infrastructure adapts. This is the promise of urban autonomy, a city that continuously adjusts itself. But autonomy requires authority. An automated system must be allowed to make decisions. Which roads receive priority? Which areas receive energy? Which vehicles move first? Which resources are allocated where? The more decisions become automated, the more important the underlying rules become. Because an autonomous system is only as neutral as its objectives. Optimize for speed, and another outcome may suffer. Optimize for efficiency, and redundancy may decline. Optimize for security, and privacy may become less important. The city can become more efficient, but efficiency is always a choice, and whoever designs the algorithm defines what the city is optimizing for.
Every smart city requires energy. More sensors, more networks, more data centers, more electric vehicles, more automation, more computation. The intelligent city may be digital, but its intelligence depends on physical power. This creates a new challenge. The city must become smarter without becoming more fragile. A traditional energy grid moves electricity in one direction, from large power plants through transmission networks into buildings. The next generation of smart grids is more complex. Energy can come from many sources: solar, wind, batteries, buildings, vehicles, and distributed generation systems. The network becomes dynamic. Energy moves in multiple directions. The system must continuously balance supply and demand. Artificial intelligence can help predict consumption. Storage systems can respond to demand. Buildings can reduce usage. Electric vehicles can become mobile energy assets. The grid begins to behave like a computational network. But this creates a new dependency. The more intelligent the grid becomes, the more software controls the physical flow of energy. The city is no longer dependent only on power plants. It is dependent on sensors, networks, algorithms, and digital control systems. The energy system becomes smarter, but also more connected, and every connected system creates a new attack surface. A city that can be controlled digitally can also be disrupted digitally. The smart grid is therefore both an efficiency system and a strategic infrastructure layer.
Every city produces data: where people move, when they travel, what they consume, how energy is used, which areas grow, which areas decline, where congestion appears, where demand increases, and how people interact with infrastructure. The smart city transforms this activity into information. The data can improve services, traffic can become more efficient, energy can become more precise, infrastructure can be maintained before failure. But data also has economic value. The city becomes a continuous source of behavioral information. And the more systems become connected, the more complete the picture becomes. Transportation data connects to commercial activity. Energy data connects to building occupancy. Public infrastructure connects to movement patterns. The city begins to generate a digital map of urban life. This creates enormous opportunities, but it also creates a fundamental question. Who owns the data generated by the city? The citizen, the municipality, the technology provider, the infrastructure operator? The answer is not always obvious. A company may install the sensors, another may operate the software, a third may analyze the information. The city may generate the data, but private systems may process it. This creates a new form of urban economic power. The ability to observe the city can become the ability to understand the city. And whoever understands the city's behavior may gain an advantage in predicting where value will appear next.
The modern city requires enormous investment. Sensors, networks, data centers, transportation systems, energy infrastructure, artificial intelligence, and cybersecurity. Governments may not build every layer themselves. Private companies often provide the technology. They build the platforms, operate the systems, maintain the infrastructure, and process the data. This can accelerate innovation. A city gains access to technology faster. Infrastructure can be built more efficiently. Private expertise can solve complex problems. But dependency can emerge. The city may own the streets, but another company may own the software that manages them. The city may own the buildings, but another company may operate the data layer. The city may control the territory, but critical infrastructure may depend on external technology. This creates a new question of sovereignty. Who really controls the city? The government that writes the laws? The company that operates the infrastructure? The technology provider that controls the data? Or the platform that connects all of them? The answer may become increasingly complicated because the city of the future will not be governed only through physical institutions. It will also be governed through digital systems, and digital systems have owners. This is where the smart city becomes a question of power. The infrastructure may be public, the architecture may be private, and the population may become dependent on both.
A platform connects participants, users, businesses, services, and infrastructure. The smart city may become the largest platform ever created. Citizens use transportation. Businesses use infrastructure. Vehicles use roads. Buildings use energy. Services use data. And all of these systems become connected. The city becomes a marketplace of movement, energy, information, and services. The platform can optimize the system, but it can also become a gatekeeper. If a business wants access to the urban infrastructure, it may need to connect to the platform. If a service wants to operate, it may need to comply with the system. If a vehicle wants to move autonomously, it may need access to the city's digital network. This creates a new type of urban dependency. The city is no longer only a physical location, it becomes an operating environment, and the operator of the environment can gain enormous influence. This is the platformization of the city. The city becomes a system that connects everything, and when everything connects, the value of controlling the connection increases. The future city may therefore resemble a technology platform. Multiple participants, one infrastructure layer, continuous data, automated decisions, and an operating system beneath the visible autonomy. The city may look open, but the architecture beneath it may be controlled by a limited number of systems.
The city of the future will not be defined only by its skyline. It will be defined by its architecture. The sensors beneath the roads, the networks inside the buildings, the algorithms managing movement, the data centers processing information, the systems balancing energy, the platforms connecting services, and the infrastructure coordinating everything. The city becomes a machine, not a machine with one central engine, but a network of interconnected systems. The more intelligent the city becomes, the more data it generates. The more data it generates, the more decisions can be automated. The more decisions become automated, the more important the operating architecture becomes. This is the master blueprint of the smart city. Observe the environment, collect the data, build the digital model, predict the future, automate the response, and continuously optimize the system. The promise is enormous: less congestion, more efficient energy, faster services, better infrastructure, and a city that can respond to problems before they become crises. But every efficiency creates a choice. Every system creates a dependency. Every connection creates a point of control. The smart city may be safer, more efficient, more sustainable, and more convenient, but it may also become more centralized, more observable, and more dependent on the systems that operate beneath the surface. The city of the future may not ask citizens to understand every system. It may simply ask them to trust the architecture. Trust the algorithm. Trust the network. Trust the platform. But the architecture will still make decisions. It will decide how resources move, how traffic flows, how energy is distributed, how services are accessed, and how the city responds. The most important question will therefore not be, how smart is the city? It will be, who designed the intelligence? Because the city is becoming programmable, and whatever can be programmed can be optimized, measured, controlled, and redesigned.
The future of urban power will belong to those who control the layers beneath the visible city. The data, the networks, the cloud, the energy, the operating systems, and the algorithms. The skyline may belong to the city, but the intelligence beneath the skyline may belong to someone else. And when the city becomes an operating system, the owner of the operating system gains influence over everything that runs on top of it. That is the real transformation. The city is no longer simply a place where systems operate. The city itself is becoming the system. And whoever architects the system architects the future. Next era: decoding systems, architecting wealth.